Today's speaker is Aritra Sarkar. He's a postdoc in the quantum machine learning research group by Sebastian Feld. And he will give an introduction what his current research is in his presentation. But let me give you a little bit of background, as usual, about the speaker. So Aritra, before he was a postdoc or a PhD student, he worked actually for India's National Space Agency. So he developed a few codes, and a few codes are still on some satellites, and one, I think, it made it even to the moon, if I'm correct. Yes, two of them actually. So you see, he has a very interesting background. And in 2016, he switched then gears, coming back from outer space back to the ground surface. Temperature, he didn't change too much, so quantum computing is still at low temperatures. We even get to a bit lower temperatures, but he started working on the world of a tiny quantum, and joined TU Delft in the quantum computing engineering master's program. And Aritra was actually one of the first researchers here at QuTech who was really focused on quantum algorithm and how it influences the design of quantum qubits, quantum circuits. For his master's and afterwards also his PhD, he developed first of the kind quantum algorithms for use cases, for example, in bioinformatics or reinforcement learning. And with that, I've taken already too much time, so please come in front. And we're looking forward to your talk. Thanks.
Thank you, Max, for the very kind introduction. So today I'll be talking about optimal quantum firmware design. But like Max said, I'll give you a brief overview of my career and what perspective I'm using to look at this particular problem. So I come from quantum computer engineering, and like Max said, I have a background in building computers or embedded systems for space robotics and satellites. And when I changed from that to quantum computers, there's one more thing that remained same other than the temperature, and that's both these systems are still coded in very low-level languages. Both uses assembly-level languages. And because these systems, the space systems, are so kind of constrained that you have a hardware and you cannot go and service it in Moon, for example. So you have to really test the systems out and use as much hardware logic as possible for whatever you want to do. So that kind of remained same even for the work that I did in designing the quantum algorithms, really push it to the boundaries of complexity. And later on, kind of expanded out from genomics to other fields like reinforcement learning and quantum agents learning quantum environment. In my postdoc over the last 2 years, I have shifted a little bit from quantum algorithms to making systems that enable quantum algorithms to run better on a hardware. And we call that the quantum computer architecture. And it has many different layers that I'll be talking about. But mostly I'm using these tools that I've used before for quantum algorithm design, like quantum information theory, algorithmic information theory, and explainable AI. To also design this quantum systems better. So these are theory tools that I'm using for a much more practical purpose. Okay, so the topic for today's talk is quantum firmware, and what exactly is that? So on one side, we have the physical manipulation of quantum hardware, so all the qubit technologies. And on the other side, we have the mathematical abstractions of quantum algorithms. So pretty much everything that bridges these two together is what I would like to call quantum firmware, and there are other names for it like quantum system software. And just to make our lives simple for the researchers, we have kind of divided them out in stacks. So we call them the stack layers. And here you kind of see a list of some of these. So every time, let's say your laptop says you have a Windows update, it does something, right? It installs some software, and you're not even aware what exactly it installed. It says that, let's say, it updated some virus definitions or such. And so these are basically like system softwares, the softwares that the users are, we don't want them to be aware of. They kind of upgrade your system, they make them better. But from the user perspective, everything is a system, right? From as a platform. So today I'll be concentrating on three different layers in this stack, the ones in blue. And I'll be talking about three different projects that involves one of these specific layers. So why did I choose this specific layers? And that again has to do with how do I bridge the world of algorithms with the world of hardware. So if you look at the tools that I use to, let's say, describe the hardware and the algorithms, on the hardware side, we have things like Hamiltonians or super operators or decoherence time. Whereas on the algorithm side, we have things like unitary gates or noise models or complexity classes. And if you think about that, all of these representations kind of use continuous variables or real numbers or complex numbers. Whereas the layer in between, which we call the classical control, are made out of classical finite descriptions. And a lot of things change when the representations go from a continuous domain to a finite classical descriptions. And the same way that we kind of use the Heisenberg cut in interpretations of quantum mechanics, we can call this kind of the Heisenberg interface, where the middle layer is very, very classical, and we use the same tools. And this is not really a limitation of our tools, like the way that, let's say, David Deutsch defined the quantum Turing machine. He used precisely that the program that is run on the quantum computer is still classical. So it's always a classical program controlling a quantum system, whereas like in the Turing machine, the tape can be in superposition states. So three of these projects that I'm going to talk about is using this classical representations, this classical finite representations. So we have the, we have the quantum layer, which is at the compiler level. We have the QISA, the quantum instruction set architecture, which is at the microarchitecture level. And we have pulses, which is at the analog level. And they kind of flow nicely into each other. So we can directly give the output of the quantum to the QISA and the output from the QISA down to the pulses. And that kind of forms an entire chain of logic, right from the algorithm down to how the hardware is manipulated. Okay, so let's start with a question. Are all quantum computers alike? And this is important when we are designing this interface, because this interface now has to control different quantum hardwares using the same algorithm. And this question has different answers based on whom you ask. So to, let's say, complexity theorists, all quantum computers are alike. And there are at least two reasons for that. One is the Turing-Deutsch principle, and the other is the Solvay-Kitaev theorem. So one comes from, let's say, computability theory, one comes from complexity theory. So the Turing-Deutsch principle says that every physical dynamics can be simulated efficiently in a quantum computer, at least, if not in a classical universal computer. And we have like experiments like people trying to simulate black holes on quantum computers, the dynamics of black holes. And so initially this was, again, done for the quantum Turing machines and later generalized to the circuit model. And we have this local set of quantum gates, which are universal. And based on that, we can say like every quantum computers have the same computing capability in one way or the other. So that every quantum computers are same in computability, but it also matters how much resources it takes. And resource theoretically, the normal notation is asymptotic complexity. And again, using the base of the Solvay-Kitaev theorem, which is the iterated shrinking lemma, which is like a group theoretic argument, we can say that using any universal set of gates, we can determine how big the quantum computation will be, how much time it's going to take, or how many qubits you're going to need. And that doesn't scale really bad. It scales as a logarithmic factor of the error that you're trying to, the approximation that the circuit has. So, well, that says that things are possible using any quantum gate sets. We can find a circuit, at least in a circuit model, which is going to implement that particular computation. A small note that the Solvay-Kitaev theorem is really good, it scales really well logarithmically with the error. But with respect to the number of qubits or the size of the Hilbert space, it's still exponential scaling. So if you go and try to decompose bigger and bigger unitaries, it still scales as, let's say, 4 to the power n of the number of C0 gates that's required. But so quantum computers are kind of alike from the theoretic perspective. Tell that to an experimentalist, they're going to go crazy, because there are like a million different reasons why quantum computers are not same. And I just gave you 3 examples, but there are way more than that. At a very high level, at a very abstracted level, we have the DiVincenzo criteria, which is a criteria for engineering quantum computers. And there are like 5 of them: the characterization of the qubits, the coherence time, the universal native gate set, and initializing and measuring out the information from a quantum computer. Then we have the qubit connectivity that kind of bounds how the interaction happens between the qubits. If they're not connected, you cannot, let's say, entangle them, entangle across this chip at a very high rate. And we also need additional gates for routing, and that kind of chips away some of the gate that you used, and that's going to increase, let's say, the requirement for the decoherence time. And finally, most of the time we use random or very trivial benchmarks to even characterize our qubits, which is not true. Like, all quantum algorithms fall in certain kind of complexity, which is neither trivial nor random. So of course, there are classes of circuits like the quantum supremacy circuits, which are very random, but those cannot encode algorithms as such. So we are also doing some work using generative AI to expand this benchmarks of realistic quantum circuits. So I have listed some of the current projects in our group which are at these different layers of experimental quantum architecture. And only if I have time at the end, I might go into some of these. But today, now I'll focus more on these 2 things in red, like how does the native gate set and the maximum circuit depth that's dictated by the decoherence time happens like a trade-off, which tells you how powerful your quantum computer is. So with that, let's move to the kind of the first project that I wanted to present. And that's, again, on the quantum compiler optimization layer. So this is a project collaborated with my collaborators, Akash, Shibashish, Matthew, Tamal, Jaroslaw, and Sebastian. So like we saw in the last slide, there is a limit on the quantum circuit depth that comes from the decoherence time. And then each different QPUs have a different native gate set. And this has to be discrete for controllability. So you can have any programming language at the top layer, Python, C++, Qiskit, OpenQL, whatever. But it gives you some limit on what is the rotation angle, for example, that you can specify. You use some variable to store your rotation angle. And even if you write, let's say, pi there, it's never pi rotation. It kind of gets decomposed to some 32 digits of pi or something. So if you go into the fault tolerant regime, it's even fewer gates, which are mostly the transversal gates. And then you can have some gates that require, let's say, magic state distillation. But definitely, there are only few gates. And normally we use things like Hadamard T and C0 for fault tolerant, at least for describing the algorithms. So basically, we have a few discrete set of gates, and then there is a limit on the circuit depth. And these 2 criteria together kind of tells that universal quantum gate sets are not equivalent, at least not in the NISQ era. And we can kind of divide this equivalence into 2 different parts, just to make our life simple. And we can call it expressibility and reachability. So these terms kind of come from machine learning side. Expressibility, again, comes from computability. So the same universal gates can, in principle, explain or express any quantum algorithm. But then reachability kind of bounds how much time you're going to take. So that kind of bounds what computation you can do with that specific gate set, and that kind of breaks down. So different gate sets have different reachability. And we did a very high level study of that. And over here, we are using 2 different IBM small chip topologies, the L topology and the T topology. And we are trying to do state preparation on different quantums, like, I guess this was on 4 qubits. Yeah, 4 qubit states. And we find that one topology is better in expressing or preparing one kind of states, and while the other topology is better for preparing the other quantum states. So yeah, just a proof of concept that all gate sets are not really equivalent. So what can we do about it? Thankfully, there is a very rich theory in classical theoretical computer science that's called as algorithmic information theory. And that basically deals with the space of programs that you can write using your native, whatever is available to you. So it can be gates, it can be like the primitives of your programming language. And then you can decide what happens if you randomly write a program. So that is a kind of a weird concept that is called as algorithmic probability. So imagine that you bring in a monkey, and in front of the monkey, you put in a keyboard. The keyboard can only type valid sentences in Quasm. And once in a while, there's also, let's say, a measure instruction or an execute button, enter button. And once in a while, the monkey also presses that button, and then the quantum computer runs and gives you some output. So if you have some kind of a setup like that, what is the probability that the quantum computer will output a specific state? So that is basically the random programming monkey model. And to kind of export it and use that result for quantum computers, we had to kind of extend it to the world of quantum computation. And at least in the circuit model, that becomes the quantum circuit probability. And the second one is Kolmogorov complexity. So again, this has already been extended to the quantum world by other researchers. And the Kolmogorov complexity is the smallest program that you have to write so that something is generated. So this is basically the smallest. And if you think that the Quasm is the smallest program that you can write, think again. Like, let's say if you have a Groover search, you are not going to manually write every, let's say, the oracle and the diffusion block that many number of times. You're going to put it in a high-level loop, and you calculate how many times the loop has to run based on the number of solutions and the size of your search space. And then you're going to make the computer unroll that for you. So that's like a high-level representation of Groover search. And Kolmogorov complexity or description complexity in general is just how many bits of, what's the size of your program, like the bit length of your program. So again, this has to be, so quantum Kolmogorov complexity kind of says that most quantum states have exponential length decomposition. So it's very few states which are reachable using a very small representation. And this kind of comes from number theory, because most numbers require very long descriptions using any like representation. So if you, let's say, have Boolean using a length of 2, so let's say you can only use 2, you can only express 4 different numbers, 0, 0, 0, 1, 1, 0, 1, 1. And similarly, using, let's say, a decimal representation using 2 digits, you can go from 00 to 99, not more than that, right? So for 100, you'd need 3 letters. So exactly the same way that if you bound how many digits you can use, you can only go up to a finite number of numbers and not up to the full real line. Whereas the Hilbert space, again, is continuous. So it's kind of the same argument holds that with a finite circuit, you can only go up to certain places. So we are using this theoretical argument for designing a quantum compiler. And the quantum compiler is called YAQQ. It's kind of inspired by the YACC, which is a classical compiler generator. And the reason why we call this is because it's kind of quantizing the way to parse the quantum Hilbert space. And what it does is we can use it like a normal compiler. You give it any gate set and any unitary is going to decompose it. It will most likely be an approximate decomposition because of the quantum Kolmogorov complexity. You can give it 2 different gate sets and give it a set of unitaries. So let's say that set comes from all the algorithms that you want to run from the benchmarks. And then you can compare which gate set is better. This can be like used for comparing two different available QPUs. Let's say take the native gate set of INQ and the native gate set of IBM, and you can see which of them are more useful for the particular application that you have. And the third one is what it's actually designed for. So you can give it a specific gate set and a set of unitaries, and it's going to find for you a different gate set that's better for at least the set of unitaries that you have given. And the better is kind of represented by the process fidelity of the unitary decompositions and the circuit depth. So this is like how we envision it to work, and I'll show some real experimental results in the next slide. So let's say the blue line is the original gate set, let's say Hadamard TC0, and I'm using it to decompose 20 different random unitaries. And after searching through this space of quantum gates, it finds some other gate set, and then if you use that gate set to decompose the same 20 unitaries, it has a higher process fidelity, the red line, for example. And on average, obviously, the process fidelity is better. And what's also important is the trend is kind of different. So wherever the blue performs really bad, the red is good. But there are also the points the other way around where the red performs worse than the blue one. And this comes from like the no free lunch theorem from machine learning. And this kind of similar trend can be seen in the circuit depth. And in this particular case, there's also like a trade-off. So if you have a better process fidelity, most of the times, the circuit depth is also higher. And but we did some experiments and we got some results where we are able to optimize both of them. So we have a better fidelity as well as a lower circuit depth. And these things, the weightage of the circuit depth or the process fidelity, or how much weight am I going to give to make the two gate sets really different from each other? So this is like a tunable cost function that we can use and run this program. So let me show you some of the experimental results. So these are like 200 different high random points on the block sphere. And so this is how, let's say, the result looks like. So the blue one is decomposing this 200 points using the Hadamard and T and its dagger, since the Solvay-Kitaev theorem uses that. And then we found two different unitaries, the ones in red, which has a much higher fidelity, but also a much lower circuit depth. So this fidelity is not because there's noise in the system. So both of them are run on noiseless system. This fidelity is because the circuit itself is an approximation of how much you can reach. So you're going to get an added benefit from the circuit depth because now the circuit depth is also lower, and that's going to reduce some of the errors in the system. So you're going to, like, they are both the good things are kind of going to add up. What do the gates look like? They look very random, but these gates can be prepared on most of the quantum systems on IBM. They can be decomposed as, of course, 3 different rotations. And so it's not a question of making a native hardware using these gates, but if you can control, if you want to express your circuits using only a few set of gates, it's better to choose these gates and try to find, let's say, transversal versions of error correcting these gates, because they are much better in expressing the unitaries that the circuit demands or your algorithm demands. And so once you optimize that on single qubit 200 unitaries, that same gate sets can now be used to decompose bigger unitaries. So now we extend it using, like, we add C0 to the set to both the sets. And now we are able to, like, we decompose very less, like 220 unitaries over here. But we can see, like, the red gate set, like the one that we find, has a much higher fidelity in decomposing the 2 qubit unitaries now. And one more small experiment is where we've tuned the cost function to focus more on the novelty. So the blue gate set is the Hadamard T, and then we have a different set of 2 qubit, like single qubit gates that we found, the red one. And over here, the focus is more on getting a very different trend line. And in principle, then what you want is, if your algorithm runs better on the blue gate set, use that QPU. And if your algorithm runs better on the red gate set, then run whichever QPU has that as the native gate. And so this is available as a Python package. I'm welcoming all of you to install that and try it out. We have tried to make it as user-friendly as possible. So there's like one single configuration file where you can run everything, like give all the specifications and it's going to run. This work is not fully new. There's another tool that exists that's very similar to this, and that comes from the Biscuit, like the Berkeley Quantum Synthesis Toolkit from Berkeley Group, and Inflection, which comes out of a spinoff from Chicago. They have something called as a Superstack, and Superstack has a feature called BYOG, Bring Your Own Gate Set. And the feature is kind of similar of the BYOG using Qiskit if you use the YQQ for this. And right now we are already using YQQ to enable other projects in the group. For example, we are comparing it with the unitary decomposition native in OpenQL. We are using it to benchmark different error correction codes and also for the project that I'm going to talk about next. So let's move down a layer, one layer lower, and let's go to the quantum microarchitecture optimization. And so this project, I have my collaborators, Shibashish sitting right there, and Sarang and Sebastian, of course. So quantum computers requires resources to run. And most of the time we talk about time and space, which is like the gates and the qubits. And these resources have been used to define the other metrics like quantum volume, which also has a bound on how much noise it can have. But these are like the most used in circuit complexity theory, where we are talking about the asymptotic scaling of these resources. But there are other resources, some of them like fidelity, energy, and description complexity. And again, in the theory world, before I bring it down into some practical tool, let's explore the theory world a bit. And in the theory world, there are already some proposals of metrics that look at the other resources as well. For example, the total complexity idea from Brown and Susskind, they talk about the quantum circuit complexity and the quantum description complexity. So this is where we combine time, space, and the description complexity. There's thermodynamics of quantum computing from Zurek and Kolchiskin. And over here, we have something called as like, what is the entropy generated when a specific input state to output state transition happens. And we have a term called this KP, which is basically the protocol complexity, which is again like a description complexity of the quantum algorithm or the algorithm that does this state transfer. And again, in the classical theoretical computer science world, we have logical depth, which is also called as physical complexity from Charles Bennett, which looks at kind of a balance between fidelity and description complexity and the time. And we also have the Levin complexity, which is an approximate version of the Kolmogorov complexity that I talked about before. And that takes into account the length of the program as well as a logarithmic of the time. So these metrics do take into account all of them. And again, inspired by this, we want to make them into a practical tool. And to do that, what we are proposing is a complex instruction set architecture for quantum computing. And the reason to make it complex instead of the simple one, the reduced one, is to make it more energy efficient. So the reduced instruction set architecture, you can think of just having Hadamard TC0, like just having a minimal set of universal gates. But most of the computers, of course, we have many more gates available to the programmers. And why not choose that to make the computer more energy efficient? So what exactly is energy in terms of quantum computation or quantum circuit theory? And that comes again from the description complexity of the circuit. And like in the previous theory papers that I mentioned, it kind of relates to the least number of control bits that needs to go from the compiler to the processor to prepare the quantum state. And so if we can reduce that, the number of bits that goes from the compiler for performing the quantum computation, that's going to reduce the amount of energy required for doing that quantum computation, at least at the control level. And then I'll come how to reduce that at the processor level. So this is already being done in the classical electronics world, specifically for low-powered embedded systems. So things like IoT devices, they try to modify the assembly language that's used within those systems so that they take less power in the instruction fetch and decode cycles of these processors. And we can do the same for quantum computing. Of course, we are not limited by low power. A lot of power goes in just cooling that system down. But a lot of lines, like a lot of signals, run between the room temperature control and the digital control, the cryo FPGA in the quantum system. And these lines are really costly in terms of energy because they are connecting two very different temperatures. And if you can reduce the bandwidth required on that line, that's going to really make a lot of difference in how many, let's say, qubits we can squeeze into that system now. And we already have some numbers from our cryo FPGA group, and we know like it takes something about 2.46 picojoule per bit. And if you can reduce then and compress that circuit further, that's going to help. So what we propose is try to design and KISA a quantum instruction set architecture such that it takes away this bandwidth requirement a little lower. And then that comes again from the classical coding theory, which is all about like lossless compression and also lossy compression. And let's say for the Morse code, we use something like the E and the T are most frequent alphabets in the English language. So they have small codes. It's just a dot or a dash. And it's kind of the similar idea for quantum programming languages as well. And so this is a plot where we directly took the QUASM codes for 10,000 different samples, and we compressed them using a simple classical compression algorithms like the BZIP2 and the BZIP3. So we can compress quantum cores, that's a good thing. But the problem over here is microarchitecture or a quantum controller won't understand QUASM files because QUASM files are typically ASCII files and they are basically .text with a different format. And so we need some encoding that is already understandable by the FPGA or the ASIC within the controller. So that's the next step that we are trying to do now. First, like very basic way to do that is we have this native gate sets, let's say Hadamard T and T dagger to make Solvay-Kitaev work again. We can directly encode that in binary. So Hadamard is 0, 0, T is 1, 0, and T dagger is 1, 1, let's say. So that's going to remain constant irrespective of how many times Hadamard T or T dagger is used. So we can do slightly better. And we can Huffman code the native gates. So that's a way of optimal coding based on arithmetic coding. We can figure out what's the frequency of using Hadamard T and T naught, exactly like the Morse code. And we assign a code which is smaller. Since Hadamard has the highest frequency, we give it a smaller code. So Hadamard is just 0, and T dagger is 1, 1, and 1, 0. For this to work, it has to be like a prefix-free code so that just from the prefix, we can understand and decode it. We can do even better than that. So instead of the native gate set alone, the way that normally unitary decomposition is done is it uses a kind of, it expands the basis in what's called as a Solvay-Kitaev basis approximation. And instead of just using Hadamard and T, it kind of makes them into a small sequence. Over here, it's done for a recursion depth of 4. So that gives you sequences of depth 4 at max. And then we can do the same thing, the Huffman coding on the frequencies of this sequence. And this is how that looks. So we see that most of this encoded ones are not even used. So, but some of them are used. And we see like, let's say Hadamard is, well, not used so much. So every time Hadamard is used, it's used along with some other T dagger or something else. So from this chart, which kind of also plots the mean and the standard deviation and the median as well, we can kind of put a cutoff of which things we need to encode to make the controller understand. And that's the idea is we put in a cutoff that we are only going to encode the top blue things on the figure on the right. And everything on red, we are not going to encode. So we are going to just decompose it back to the native gate set Hadamard TC now. So if we do that, we find that we are able to achieve a much higher compression ratio than that can be done by just encoding the native gate set. And so now we are not only just doing coding theory, we are doing what's called as concept discovery. So imagine that in a quantum algorithm, we use a lot of times entangling operations. So we create bell pairs a lot of time. So why not make bell pair primitive instruction that you can give to the hardware and that directly understands that it needs to work on, it's like a 2-qubit gate and it does the entire bell pair operation. So Hadamard plus C0. So this is, again, in the world of machine learning, this is called as concept discovery. And it's kind of learning which things you need to have in a language, which words are useful in a language. And if that word is not useful, that language just doesn't have it. Yeah, so now we are trying to extend it. So these are the results for just 1 qubit operations. We are now extending it to multiple qubits, and we are using like the YAQQ to also do the decompositions for this. Great, so let's move on to the last project. And so over here, we have encoded the best way, like we have reduced the energy from the compiler down to the controller in the hardware. How can we reduce it further? And that comes from the pulse optimization. So this is at the controller level, and most of the pulse optimization are done for fidelity. And over here, we are trying to also bring in energy. And this project is done in collaboration with Sebastian and Sebastian. Sebastian sitting there. And this also has a very nice associated theory with it. And that comes from quantum speed limits, which kind of tells you the fastest way of doing stuff on quantum computers. And there is already some work done on making energy equivalent to the fastest way of doing computation. And that comes from every quantum operation, every quantum computer can be thought of in a geometric way on the corresponding Riemannian manifold. And the geodesic on that manifold is basically the shortest way of doing that computation. And that kind of goes into, it kind of has the same units as a Lagrangian mechanics. So it's basically energy times the time. And what that research says that it is optimal if we move along a constant angle at a constant angular momentum. The only problem is this is in a world where the drift Hamiltonian itself can be adjusted, which of course we cannot. There is like natural frequencies for the qubits. And so we have something called as accessible controls. Even though there's an absolute geodesic, which gives you the shortest path for doing the computation, there is further limitations from the control signals that you have. What is the accessible geodesic? So now this work doesn't make use of the energy optimization, and we are trying to do both of them together, find the accessible geodesic so that we minimize the energy of the quantum computer. And so this comes under the domain of optimal quantum control or pulse level gate synthesis. And the most popular algorithm for that is, well, there are quite a few different algorithms like GRAB and GRAPE. So we are using GRAPE, which is gradient ascent pulse engineering. And the first thing we find that there's, of course, a trade-off between fidelity and energy. So if we try to reduce the fidelity, we have to spend more energy. Whereas what's more interesting over here is based on how you tune the system to focus more on the energy or the fidelity, it's better to sometimes use a higher energy version or a higher fidelity version. So let's say if you have let's say the red lines are much more spaced out, while the green lines cluster more towards the energy cost of 1. So overall, there is like a Pareto frontier, which tells you how to adjust the energy and the fidelity in such a graph. And we kind of extended the grape to also take into account the energy metric, and we were like designing pulses based on that. And the good thing is it kind of converges. So we do find at some grape iteration, we are able to minimize the gradient. So we do see some kind of optimal behavior for the pulse. But what we need is in the next era, we also want to learn from the pulses by performing an experiment. So we are working on a noisy computer, and if we just use grape for designing these pulses, we are kind of clueless how it will perform in a noisy system. And grape doesn't necessarily allow you to take into account the feedback from an experiment like the density matrix, for example, and adjust based on that. So that's the next step. And we are basically trying to do this, use deep reinforcement learning agent that learns a pulse level unitary for a noisy quantum processor. And this is the system that we have. So we have the EO grape that we saw in the last slide. And the result from that, we are feeding into a neural network. And we are training the neural network to replicate that grape pulse. So after a certain iteration, the green neural network kind of learns how can it replicate the pulse that comes out of grape. And then we take that neural network and feed it into a noisy quantum system and see how that performs. So now we get 2 different rewards from the quantum computer. One is the reward from the fidelity that you see on the lower side, and then also a reward for optimizing the energy. And we can tune those weights separately based on what we like to do. And what we see over here, some plots for this is if we do this particular method where we use the grape to train and kind of kickstart the system, we get an optimal value for both the energy and the fidelity. Whereas if we do not do this, what's called as without warm start, so if we directly feed in the unitary and tell it to learn and optimize both fidelity and energy, then it doesn't work so well. And it still kind of reaches the similar kind of fidelity in optimizing the fidelity, but then the green curve is where the energy cost increases a lot. So kind of we show from this experiment that it's possible to jointly optimize both energy and fidelity for a quantum system. And what you see over here on the x-axis is both like the episode of the learning, but also the noise is increasing from the noise temperature. The decoherence time for every episode kind of decreases. So it goes from 200T to 20T. So it's basically increasing the noise. And currently we are extending it to a universal set of gates. So what you saw from the previous experiment, like finding the minimal expression for describing a quantum computer, then we can use those specific gates which are selected by that second project, which are really good for encoding, and use them in this at the pulse level and dictate our quantum computing. And there are certain quantum compilers which directly control at the pulse level now. So you can even design variational algorithms from the pulse level. So that means that sometimes we directly need to send pulses from the compiler to the quantum processor. So that means that we can also should look at compressing the pulses, just like we were compressing quantum algorithms at the circuit level. So that's up for the future plan. So basically that brings me to the 3 different projects and how they fit in with the rest of the stack of the quantum firmware. And at the top, we have, okay, so this red ones is what I talked about today, but there are a lot of different other projects which are going on in the group. For example, at the top layer, we have a project called Art-A, which tries to find a nice setting for defining the compiler characteristics of a spin processor. Then we have a list of benchmarks, the QBench, and a generative AI like that uses generative pre-trained transformers, GPT. that generates more and more benchmarks, which are still realistic. We have a project on automated discovery, automated quantum machine learning. And then we have the SpinQ compilers specifically for the spin processors. And we have a project of the in the routing and mapping, which is on in the NISQ processor. So most of the mapping algorithms do not take into account the 2-qubit gate fidelities between each of the nodes. And we can use that to make better mapping choices. And there's also a von Neumann entropy-based quantum circuit mapping. Then we have the complex instruction set quantum computer. We have a project on automated discovery of quantum error correction codes, and of course, the holographic quantum error correction code. The energy optimized pulse engineering is what I talked about in the third project. And then we're also working on machine learning for gate set tomography and machine learning control for quantum computers. So without characterizing, can we also control a quantum computer? So as you see that it's many different levels of different projects that we are working on our group. Of course, it's not possible without a super nice team that's led by Sebastian. And these are all the collaborators at all these different layers. But most importantly, we are also looking for collaborators more from the hardware side from QuTech, so that we can test some of these ideas that I presented on real. With that, I would like to end my presentation. Thanks for listening.
Thanks for the talk. So now the question session is open. Are there any questions from the audience?
When you talk about the optimal gate set, is the optimal gate set depending on the choice of state you use in the experiment?
Choice of what, sorry?
Could you go back to the project?
This one?
Yes. Like the two optimal gate you find, is it depending on like the training set you are using, or is it true for every possible state?
Yeah, so it is dependent on the training set, and that is basically what we want to harness. So if we try to make this training set bigger and bigger, we suspect that all the quantum gates should be similar in performance, only because we are not using it for a very representative set. But that's also true that we are not going to create all different kind of unitaries in a quantum processor. It will be based on, let's see, the algorithms that we want to run. So definitely this kind of tool will be most useful if we make, let's say, something like a application specific quantum computer. So quantum computer that runs only shores, for example. So then you have mostly the same type of unitaries. But like at least for this set, we are seeing like even if we increase the number of random points to, let's say, 500, it kind of still gives the advantage. So yeah, so like I think there will always remain a balance. Like there will be some states, like let's go back to the slide where, yeah, this slide. So I think if we increase the number of unitaries too high, like we really increase it to near like infinity, then there will be still this variance since we are limiting the number of operations that we can run. So there will be some states which are easier for one gate and other states which are easier for the other gate. But on average, they will be the same. So this difference between the straight lines, the average will kind of diminish. But we are still going to have one gate set better for one set of unitaries, the other gate set better for the other set of unitaries, except that they are going to be equally good or bad over the full range. So that's kind of like the no free lunch here. Yeah. Any more questions?
I have a question. I'm a little bit confused about the energy efficient. Like in one of the project, people have worked with to minimize the energy consumption, something like this. Have you given some promising result compared with the previous one, like how much energy you have saved? Have you found any good result in terms of energy consumption?
Yeah, so at least for the second project, so you have this number, which is like the energy consumption, like the energy budget or the energy per bit in the transmission line between the room temperature and the cryo layer. And this number, like picojoules per bit, can directly be translated to this graph over here. So this is like the compression ratio graphs. So if you can save that many number of bits, that directly translates to the number of picojoules or joules that you can save. Obviously, that factor is way different, like way smaller than the total energy required for cooling. So this doesn't make quantum energy efficient quantum computer, but it reduces the noise or the energy budget for the computation. It gives you more energy budget to have to squeeze in more qubits on a quantum chip. And it gives you like every less bit transmitted reduces the noise in the quantum computation.
Can you do quantum error correction at the pulse level?
I'm not very sure, but there is something called as automated quantum error correction. So I think that has to do with designing the pulses so that they are more error tolerant, but yeah, it's not really my field. I don't know that. Yeah.
Is there like a no lower limit on how much energy you need to use to perform operation, and is the algorithm return the best lower bound?
That's a very nice question. So in principle, quantum is reversible. So in theory, it should be zero energy computation till you measure. But like we have this direct relation between the geodesic, which I talked about, I think in the next slide, and the energy required to do the computation. So the speed limit kind of also bounds how much energy is required to do a quantum computation. So there is an energy cost because you have to drive some Hamiltonian to perform that quantum computation.
Is this energy here directly correlated into the bandwidth of the signal? If you say that higher, for example, frequency generates more energy, or that sense?
Yeah, so like at least in this one, we have one thing is we have the picojoules per bit, but the other one is the bandwidth of this transmission line. So let's say 40 Gbps. So if you have less bits to transmit to the system, you can also reduce the clock speed of that transmission line. And most low-level electronics clocks take a lot of the energy because they have to go on in every cycle, whether you want to send a signal or not. And if we reduce the total amount of bits sent to the cryo layer, we can use a lower frequency clock, and that's going to also add to the energy saving.
What I meant, sorry for misconfusing the word bandwidth, what I mean with the signal line, which also has some transition line, some cable, also has a bandwidth. Typically, it consumes more power at maybe higher frequency or lower frequency. It's not. Could you also include that, or is this included in this in the optimal control? For example, if the ratio between energy and between frequency of the signal and energy consumption is not linear?
My guess is no. So So the only, let's say, the frequency term that we have right now is for the drift Hamiltonian. But also, I don't think it will be too hard to modify the current system that we have to also include further limitations on what we can form. And yeah, so we are also limiting, like we are, let's say, not exactly the same, but what we're trying to do is how many time slices can you use for the pulses. So of course, it learns better if you use less time slices, but then the control is also very rough. And then if we increase like decrease the size of the pulses, then it's much more smoother and it's much more better and much more energy efficient in a way. Yeah. Thank you.
More questions from the audience? Are there online questions? Maybe checking. If there are no more questions, I will close the session. Let's give our speaker a very big